Hello everyone, this is Sid from Sony. In this video, I'll be sharing in-depth details of a paper titled DeFace, Learning to Decouple the Lights for 3D Face Texture Modeling, which was presented at NeurIPS 2024 last year. In this paper, authors introduce a novel approach to model 3D facial textures under challenging illumination affected by occlusions. The theme revolves around the task of face texture modeling by effectively decoupling lighting influences from reconstructed 3D face textures. Summarizing the two key contributions of the paper. First, DFace presents a new face texture modeling framework by learning to separate the environmental lighting effects from intrinsic facial features into multiple light conditions with neural representations. Second, the authors propose realistic constraints to help improve the authenticity of texture by introducing human face priors. More about the theme of this paper. The task of face texture modeling involves estimating 3D facial geometry, usually a mesh, and its corresponding textures from a given input face image. The key challenge tackled by such methods is capturing fine details while ensuring the consistency under different lighting conditions. An extension of this theme is the research domain of decoupling lighting effects. In face texture modeling, it involves disentangling lighting variations from facial features to enable accurate reconstruction and manipulation of facial details under different lighting conditions. For realistic reconstruction, it becomes necessary to decouple the lighting from facial features, as lighting variations can significantly alter the appearance of facial textures, leading to inaccuracies in 3D modeling. Also, existing methods often struggle to separate lighting from texture, resulting in models that do not generalize well under different illumination conditions. Briefly covering the related works, these fall across two categories. First is the texture modeling with diffuse-only texture map. Such methods harness the power of GANs and deep CNNs to reconstruct the facial texture and shape from single images by treating it as an image generation task. However, as shown in this figure, they bake both shadows caused by self-occlusion of the nose and external occlusion of the hat onto the texture, thus causing the rendered output to appear unrealistic and lacking authenticity. GANFIT is one such method which learns a powerful facial texture prior from a large-scale 3D texture dataset, enabling reconstruction of high-fidelity facial textures with high-frequency details. To improve robustness and expedite the fitting process, the paper proposes a novel self-supervised regression approach, enhancing the efficacy of the nonlinear optimization involved in reconstructing 3D facial geometry and texture from single images. Next category consists of methods which implicitly model the influence of self-occlusion by combining local reflectance texture model incorporating diffuse, specular, and roughness albedos with ray tracing render. These methods can create more realistic rendered output and avoid the shadows of self-occlusion on the recovered texture, as shown in the blue region, but struggle with the influence from external occlusion like shadows, as depicted in red region. Paper titled Practical Face Reconstruction via Differentiable Ray Tracing is one such method that estimates 3D geometry, reflectance properties, including diffuse, specular, and roughness, pose camera parameters, and scene illumination from monocular images using a differentiable ray tracing approach. It employs a coarse to fine optimization process, systematically estimating subsets of parametric attributes to achieve consistent and semantically meaningful face reconstructions under unconstrained illumination, as well as self-shadowing conditions. To mitigate the above-mentioned issues, DeFace is proposed as a Category 3 method, which uses multiple separate light conditions to imitate the local illumination of different facial areas after being affected by external occlusions. As shown in the figure, their method can model the influence from external occlusion as one of the light conditions and eliminate its effect on the recovered texture as highlighted in the red region. Specifically, it uses a spatial temporal neural representation to predict masks for different lighting conditions, which are used to combine rendered results under multiple light conditions into a final output. Let's take a deep dive into the architecture of DeFace. Given an input image or video sequences IN taken from affected illuminations, the task is to recover clear and accurate texture T from IN and ensure that T can synthesize results I out close to IN alongside 3D statistical coefficients alpha, beta, delta, P, and gamma. Instead of assuming that the face is exposed to a single and uniform illumination, they propose to model n possible separate light conditions, gamma 1 to gamma n, in the environment, where the masks for possible regions Mn are predicted with a neural representation F. Authors use the statistical coefficient delta from an off-the-shelf 3D called albedo to initialize the face texture T and optimize neural representations. Render mask MR and faces IRN under N light conditions are acquired through ray tracing rendering. F and G are neural representations predicting lighting mask FMN and facial region mask MO. Effective masks ML and rendered faces IRs are selected from original MN and rendered IRN during optimization with adaptive condition estimation or ACE strategy. IRs are combined into IR with ML, where IR is merged with surroundings in IN with MO to construct output image I out. The face shape is modeled with statistical coefficients alpha identity, beta expression, and P pose parameters. L4 and LLAN are photometric loss and landmark loss respectively. The pipeline of the entire training process is presented on this slide. The training consists of three stages. In stage 1, the expression beta, shape alpha, and pose p coefficients are optimized to construct the basic face shape. In stage 2, all coefficients and the neural representations f and g are optimized together to reconstruct the face with statistical model. In stage 3, the texture T is directly optimized without coefficient delta, while gamma and F are optimized with small learning rates. The weights are all predefined, and authors use Adam Optimizer for optimization. Before diving deep into each component and proposed constraints, I wanted to share a few prerequisites. First is the concept of spherical harmonics. It is a method of illumination modeling which replaces parts of lighting equations with spherical functions that have been projected into frequency space using the spherical harmonics as a basis. They can represent complex lighting environments by decomposing the incident light into a series of coefficients, allowing for efficient computation of lighting effects, such as shading or shadowing in real-time rendering. They are categorized by two indices, degree and order, determining the frequency and orientation of the harmonic. A grouping of functions that share the same degree form bands. Next is ray tracing, which generates computer graphics images by tracing the path of light from the view camera, which determines your view into the scene, through the 2D viewing plane or the pixel plane, out into the 3D scene, and back to the light sources. As it traverses the scene, the light may reflect from one object to another, causing reflections, be blocked by objects, causing shadows, or pass through transparent or semi-transparent objects, causing refractions. All of these interactions are combined to produce the final color and illumination of a pixel that is then displayed on the screen. The primary advantage of ray tracing over rasterization is its ability to produce significantly more realistic lighting effects, including reflections, shadows, and refractions, by simulating the actual behavior of a light in a scene, resulting in a much more immersive and lifelike visual experience. DeFace uses a general-purpose, off-the-shelf, differentiable ray tracing renderer called Redner that is capable of handling general light transport phenomena. It generates gradients with respect to the scene parameters such as camera pose, material parameters, mesh vertex positions, and light parameters from a scalar loss computed from the output image. Back to the model, following a method called nextPhase, DPhase utilizes 9-band spherical harmonics and ray tracing rendering to model the illumination under self-occlusions. They use n separate SH to model n possible light conditions. The coefficients are then simply initialized as the following equation on the right side, where I is a matrix of ones with the same shape as the SH coefficient. Please note that they use each spherical harmonic to imitate the local illumination after being affected by the external occlusion instead of the global natural illumination. This means that they do not need to consider physical influence of occlusion in each spherical harmonic. Instead, it optimizes each spherical harmonic independently to directly imitate the illumination in different phase regions. To decouple the illumination into multiple light conditions, authors design a pair of spatial temporal continuous neural representations to segment the face into regions for different light conditions. As illustrated in the figure, spatial positions x, y, and temporal position t of pixels are normalized and embedded into a coordinate system. T is decided by the number of frames in the input. Two MLPs are used to predict per pixel probability of two types. Given the render marks IMR in the ray tracing assisted rendering, the light mask MM and face mask MO is computed with per pixel multiplication of MR with output of F and G respectively. F predicts the probability of assignment of each pixel to each light condition. G, on the other hand, predicts the probability that each pixel belongs to the face region to avoid the influence from direct occlusion such as hat or hair. The design of each of these is a simple MLP with n layers, having embedding as input and respective mask as an output. As the complexity of illumination is mutative in different surroundings, authors design a strategy to estimate the number of light conditions existing in this environment during optimization. Specifically, light masks with larger area than a predefined threshold in Mn are preserved in Ml, while smaller ones are dropped with corresponding light conditions and not further optimized in the later iterations. Given the number of light masks Mn, same as light condition n, regularization L area is introduced to encourage the area concentration on fewer masks. To ensure each light condition is mainly contained in one mask of Ml, a binary regularization term Lbin is introduced to ensure that the predicted probability for each light condition tends to 0 or 1. In is the number of pixels in the mask, and small m denotes each pixel value in the ith light mask, ml, and L is the number of masks in ml. The Grober prior constraint is used to ensure the consistency of overall hue between optimized texture T and initialized texture T0 from the 3DMM statistical model calculated with delta. As the colors mainly come from diffuse albedo in T, authors estimate the overall hue of T0 with k-means algorithm on its diffuse albedo T0D and get a 4x4 color matrix C. Given the diffuse albedo of texture T as Td, this term is given by the equation on the slide. The local prior constraint is used to ensure the local smoothness of optimized texture T by constraining its local variation to be similar to T0. Diffuse, specular, and roughness albedos of texture T are then defined as Td, Ts, and Tr. And as the next step, we set the local variation of Td, Ts, Tr as Nd, Ns, and Nr, which are computed with 5x5 neighbors around each pixel, using the formulation on the slide. N0D, N0S, and N0R are local variations calculated from T0 texture. The local prior constraint LLP is then defined as the following equation. Human prior constraint is introduced to enhance the optimization of texture T in stage 3 with a face recognition network FaceNet, pre-trained on large dataset VGG Phase 2 or Cassia Web Face. The recognition model pre-trained on these datasets is trained to classify the input images to 8,000 and 10,000 identities with different genders, ethnicities, etc. In this work, authors propose a human prior constraint by maximizing the probability that the rendered face is recognized as one of the identities by FaceNet. Defining the FaceNet as FR, the human prior constraint can then be written as the following equation, where S is the embedding extracted from FaceNet. IRs are rendered under multiple light conditions. LHP constrains the textures to be more reasonable and human-like. Listing some of the loss functions used by DeFace. First, the coefficients alpha, beta, and p are mainly optimized with landmark loss LLAN, where Qn is 2D key points detected from IN. Qn is the number of points in Qn, and Qout denotes projected 3D key points on the 2D plane. The color-related variables such as textures and lights are mainly optimized with photometric loss, where IN is defined as the number of pixels in the input image. Finally, a pre-trained semantic segmentation network is introduced for distillation to MLP-G. While probability for labels of all face components such as eyes, mouth, or nose are added together to construct a classifier H, which predicts the association of pixel at X, Y, T to the face. The distillation loss LSEG can be simply defined as the following equation. Here is the overall algorithm for the training process. As notified earlier, the input to the program is the image IN, and the algorithm generates 3DMM statistical coefficients along with texture T. Stage 1 includes iterations to optimize alpha, beta, p coefficients using landmark loss. Stage 2 performs optimization using photometric, landmark, distillation, and area loss to obtain MN and RRN. ACE is then applied to select ML and IRS from MN and IRN, followed by computing same losses on these two masks. The parameters listed here are then updated. In the final stage, texture T is extracted from delta as a separate variable by optimizing photometric, global prior, local prior, and human prior losses. The hyperparameters for the program is given on the right. For experiments, authors utilize two datasets, VoxelLab2 and CelebA Mask HQ. VoxelLab2 is a diverse video dataset combined from various internet sources. A total of 38 pairs of single images, 24 pairs of videos are used for quantitative and qualitative evaluation with a resolution of 256 by 256. CelebA Mask HQ is a large-scale face image dataset with fine attributes. Authors extract 62 single images of resolution 512 by 512 for performing qualitative evaluation. Each pair consists of source images affected by external occlusions and target images with occlusion both from the same person, where each video is sampled to 8 frames for sequence-based comparisons. To quantitatively assess the quality of recovered textures, face textures extracted from the occluded source images are leveraged to synthesize the unoccluded target images. Specifically, authors optimize source and target images separately following training algorithm. Then, keeping the face shape, pose, and illumination invariant, they replace the target image's texture with the sources and re-render it to the synthetic result. This allows them to measure texture quality by quantifying the differences between the synthesized target and the original target. Quantitative comparison employs three metrics: PSNR, SSIM, and perceptual error LPIPS. PSNR to quantify the amount of noise introduced to the generated texture. SSIM for predicting the perceived quality of reconstructed images and measuring how truthful the generated image is to the original target. LPIPS to evaluate reconstruction quality by computing similarity between activation maps of two patches using LXNet. Authors evaluate and compare their method against state-of-the-art methods D3 DFR, CPEM, next phase, and RGB fitting methods proposed in FFHQ-UV. These methods offer a wide range of diversity in terms of internal mechanism of operation, ranging from CNN-based reconstruction to parameter estimation with constraints, ray tracing-based optimization, and texture decoder for generation. All of these methods, except next phase, fails to accurately disentangle illumination variation from generated texture. Conducting evaluation of voxel up2, DeFace achieves superior results on the synthesis of target images and comparable performances on the reconstruction of source images as shown in the first table. Although NextPhase performs a little better on PSNR and SSIM, it performs the worst on synthetic target images as it actually severely overfits source images. Evaluation on video sequences showcase performance superior to existing methods on texture modeling. The figure showcases comparison on voxel up2 images. The diffuse albedo is visualized as the texture because it contains most of the color information. Most of the other methods bake shadows and occlusion to the textures, which confirm they are not appropriate for faces affected by external occlusions. Comparing on Syllabe mask HQ, as shown in the figure here, we can observe that DFace continues to perform well in the task of recovering clear textures from challenging input. Additionally, the reconstructed results exhibit a higher degree of realism when compared to the outcomes produced by other methods. Here, hours and R plus denote rendered results IR, directly overlapped onto original images, and results combined with the environments using the following equation on the slide, respectively. To validate the performances more sufficiently, authors evaluate on the single image dataset containing 100 images affected by manually creating external shadows, as well as their corresponding ground truths. DFace outperforms other methods under faces with diverse shadows. The trend is further strengthened by comparing qualitative outputs with extensive shadows on source faces. A short video comparison where the texture is smoothly imprinted across frames. Another sample. Finally, I would like to report the results of several key ablation studies performed by the authors. This slide analyzes the impact of the proposed losses LGP, LLP, LHP by comparing the rendered results under relative brighter light conditions. As illustrated in the figure, it becomes evident that the inclusion of LGP loss plays a significant role in eliminating the abnormal colors on the texture, where LLP loss effectively remove large artifacts, obviously different from human faces. LHP further reduces slight unreasonable defects with priors from pre-trained recognition model. Quantitative comparisons also confirm that each proposed loss contributes to the final performances. To ascertain the significance of neural representations employed, authors perform an analysis by eliminating both F and G from the light decoupling pipeline. As depicted in the figure, the neural representation for decoupling of light conditions F notably contributes to removal of shadow artifacts from the results. Furthermore, the neural representation G displays its efficacy in minimizing existing irregularities in the synthetic results, which achieves smoother and cleaner results. Quantitative comparisons further demonstrate that both F and G have obvious influence on the final performances. Although the former mentioned existing 3D face texture modeling methods cannot process facial shadows from external occlusions directly, there are some 2D shadow removal methods trying to eliminate the shadows directly from the image. Therefore, another alternative simple baseline is to pre-process the image with 2D shadow removal networks before the network modeling. In this section, authors introduce the most recent method with a pre-trained model to pre-process the images from feeding them to the methods listed in the evaluation section. Preprocessing with the shadow removal method indeed improves the performances of the baselines, while DFace still outperforms them. From qualitative results on the left, we can observe that shadow removal model cannot fully remove the external shadows in cases where the external shadows cover relatively large regions. Besides shadow removal, learning-based de-occlusion methods can remove external occlusions from faces by predicting these regions. Such operations also have the potential to deal with external shadows by directly treating the shadow regions as occlusions. In this section, authors conduct a brief comparison with the most recent open source de-occlusion method. The quantitative and qualitative results are presented on this slide. The metrics are evaluated on the target images mentioned previously. We can observe that the de-occlusion method loses some facial details, such as beards, as it divides occlusion regions by the distances between the input image and the reconstructed result from 3D which will also regard details hard to describe with the 3D as occlusions. DeFace treats shadows as different illumination instead of occlusions, which can preserve facial details in these regions in subsequent optimization. To verify if the external shadows can be directly modeled with more bands, SH, authors also provide quantitative results modeled with only one single global SH in 9, 12, 15, and 18 bands in the given table, where they remove light decoupling framework. We can observe that increasing the number of bands in a global spherical harmonic yields quite limited improvements. A possible reason is that external occluded shadows on human faces represent drastic illumination changes in relatively small areas, which may not be appropriately modeled as a single global spherical harmonic during optimization. To explore the influence of different numbers of n, authors conduct an ablation study for the number of n used for initialization of lighting conditions, shown in the table below. Single images from Voxlab 2 are used for evaluation. We can observe that n equal to 3 produces suboptimal results, likely because the number of lighting condition candidates is insufficient to model images with complex illuminations. In contrast, n as 5, 7, or 9 yield good and similar results, as there are enough initial lighting conditions, and any redundant ones are removed. The result for n equal to 5 is slightly better, while introducing larger n and further adjusting the hyperparameters might improve the performance. It would also increase the optimization burden. Authors study the effect of removing adaptive condition estimation or ACE by initializing MN and IRN as MI and IRS directly. As shown in the figure on the right, we observe that the rendered results I out are almost the same, while the results optimized without ACE contain multiple redundant and inaccurate light conditions in MI. It confirms that ACE can help remove these unnecessary light conditions and keep effective ones. In the figure below, authors showcase the effect of two regularization constraints, L area and L bin in ACE. As the blue region's input face is not affected by any external occlusion, its illumination can be modeled with only one light condition. L area helps remove redundant light conditions. However, only using L area may create decoupled light conditions, obviously different from the observation, as illustrated by the red region. Adding Lbin can ensure the predicted mask ML to be linearly binarized, which makes the decoupled light conditions consistent as the human observation of the input. Lastly, authors present an ablation study to confirm the effect of MLPG against directed segmentation mask from phase passing network to predict MO. The circle parts of the figure show that the pass masks may be inappropriate due to the limitation of generalizability. We can see in the first row that the rendered result IR may have rough edges and artifact colors from the occlusion, while DeFace can avoid this problem by refining the past mask with G. Moreover, some parts may be missing on the past mask. As shown in the second and the third rows, artifacts shown in these unconstrained regions. DeFace can help complete these missing regions for more reasonable results. Covering some limitations and failure cases, the primary drawback is that DeFace relies on the initialization of face texture with albedo as shown in the figure on the right. For faces with many high-frequency details, such as wrinkles, DeFace may lose these details during reconstruction. Furthermore, the optimization of multiple light conditions makes DeFace slower than other single illumination methods. It costs around 340 seconds for a low resolution image of 256 by 256 on 2080 Ti GPU, which is comparatively slower than 240 seconds of FFHQ UV. I'll wrap up the video here. Thank you.